Thanks everyone for staying on to the very end of this conference. So I'm talking about pseudorandom phenomena in finite fields. And so I'm going to talk about two results from the last few years that showed certain kinds of pseudorandom phenomena in finite fields, which are slightly more algebraic than the usual kinds of results that we see in this area. So let me start off by just stating the two results that I want to talk about. I won't be able to prove them completely, but I will give some kind of proof outline of both of them. Okay, good. So the setting is the following, wherein the finite field f2 to the n. Okay, so this is a finite field on 2 to the n elements. So just to recap, additively this is just f2 to the n, and I will often be saying f2 to the n and f2 to the n, and you should know the difference. Multiplicatively, this is a cyclic group of order 2 to the n minus 1. So this is also an important fact that we need to remember. And right, so the kind of question that I'll be looking at is I'll look at f2 to the n, and I'll talk about some objects that come from the additive world of f2 to the n. Then I'll also take some multiplicative objects that come from this cyclic group, and we'll look at their interaction with each other. And I mean, the big headline in pseudorandomness is that things like this, they don't interact with each other, and the whole goal is to prove that such a thing happens. Okay, so good. So I mean, multiplication, I mean, if you want to define it on top of f2 to the n, is just there's a bilinear map, which is the multiplication map, which maps f2 to the n to cross f2 to the n to f2 to the n. And right, so it is, and the multiplication map that comes from the finite field f2 to the n is a very special bilinear map. It's not totally, I mean, it has nice properties that make it interact well with the additive group, but in many ways it's still very pseudorandom relative to the additive structure itself. Okay, so good. So let me state the two kinds of theorems that I'm going to be showing. So the first theorem is, it will talk about polynomials in f2 to the n, and measure their correlation with multiplicative characters of f2 to the n. Okay, so let me so I'll state it, and then I'll explain what all the words in this mean. Okay, so for a polynomial p of x1 up to xn, okay, so this is an n-variate polynomial over f2, degree of p at most n to the 0.1. Consider the following quantity that measures the correlation between p and something. So we'll look at minus 1 to the p of x, where x varies in f2 to the n, and I'll measure the correlation of that with a multiplicative character of f2 to the n. Okay, so and this is the quantity that I want to say is small. Okay, where chi is, for example, the cubic residue character of f2 to the n star, and so then I'm implicitly assuming that 3 divides 2 to the n minus 1, so that there is a cubic residue character. Okay, so this is the kind of statement that so first of all, I'm going to say that this is an exhibition. This statement exhibits pseudorandomness in the sense that it's saying that this object, the multiplicative character, does not correlate with this additive object p of x, and so this is showing that the multiplicative character is pseudorandom relative to the to polynomials over the finite field. So So one question that you should have asked me is, what do I mean by P of x? Because x is coming from the big finite field f2 to the n. So what I mean is, interpret f2 to the n as f2 to the n and plug that x into the polynomial. Okay, so is the statement of what I'm trying to show right now clear? Good. Right. So what I find interesting about this theorem is, first of all, its proof is going to be somewhat non-standard from the usual way people prove character sum bounds, and the quantitative aspect of this theorem that makes it different from those other proofs is that it works with polynomials all the way up to degree n to the 0.1, while usual Cauchy-Schwarz methods would stop at degree around log n. How small is small? Oh, so small is n to the minus 0.1. And 0.1 actually stands for 0.01. Good. Okay, and there are similar statements that one can make about other objects coming from the multiplicative world. So another function that you can put inside here is -1 to the trace of cube root of x. So things related to cube roots and being a perfect cube, these kinds of things do not correlate with low degree polynomials of
and the best to hope is square root, 1 over square root n?
The best to hope is 2 to the minus epsilon n. So it would have been 1 over square root of 2 to the n, potentially. But yeah, this could have been 2 to the minus epsilon n. And if a statement like, and if 2 to the minus epsilon n is actually true, then this would have amazing consequences in complexity theory, because it would give an example of a very hard function for AC0 parity, which is a complexity class. So I'll explain the connection in a few minutes. Okay, good. So this is the first kind of theorem that I want to talk about. The second kind of theorem that I want to talk about will be about, again, so I'll take an additive object and I'll take some other object related to the multiplicative group, and I'll look at their interaction, and things will be small. Okay, so now the additive object that I'll take is a subspace over f2 to the n. So let A be in f2 be an f2 affine subspace, and dimension of A is, okay, so yeah, so there are specific numbers I have to write here to make it a theorem, but the point is that it's okay. So it's okay. So let me write 0.4 times n, and suppose A is not contained in. Okay, so okay. Actually, this thing maybe I should state after I state the theorem, so that. So, okay, so suppose something. So something has to be supposed. Then the expected value over x varying in A of the following function, -1 to the trace of x to the 7 is small. Is less than, well, sure, 2 to the minus n to the epsilon. So let me make the statement again. So I have an affine subspace. I'm looking at this particular function, trace of x to the 7. Okay, now I'm measuring how biased it is on the subspace A. Okay, and the question is, and this is saying that this is pretty balanced. It takes the value 0 and it takes the value 1 roughly equally often. Good. So why do I need to suppose something more? Well, okay, so there's something serious that happens when you talk about subspaces which are of dimension less than n over 2, which does not happen for subspaces of dimension greater than n over 2. And this is the issue of the field f2 to the n having subfields. So the moment f2 to the n has a subfield, then if you take A to be that subfield of dimension, let's say a subfield of dimension n over 2, the moment you take A to be that subfield, then you cannot hope for a statement like this in general. So yeah, so good. So that's exactly what the assumption is. So suppose A is not contained in f2 to the n over 2, let's say alpha times that plus beta. So whenever A is not contained in a subfield, you have the following, you have this kind of balancedness property. So there is the obvious counterexample to this, which is take A to be a subfield, and the moment you omit that obvious counterexample, there is indeed balance, as you would expect.
Do you mean 2 to the n minus 1?
No, 2 to the n over 2. So once you have the field f2 to the n, the only possible subfields are f2 to the n over 2 or f2 to the n over 3, and so on. And so this is right. And since we're dealing with subspaces of dimension 0.4n, there's the possibility that it's contained in. Yeah. Good. Okay. So any questions about what I'm trying to prove?
A doesn't contain a subfield, or A is not contained
it can't contain. Oh no. So if it contains a subfield, then that would be of size 2 to the n over 3, and then it's not a problem because you've gone outside it. So if A was contained inside this, then you raise that to the power 7, and it stays inside that, and then the trace of it is somehow, this trace is just a linear map from f2 to the n to f2. So this is like taking the first bit of the element. Okay. Good. So the plan for the rest of the talk is to give an outline of some lemmas or statements that come along the way in the proofs of these theorems. Okay, good. So I'll first talk about the first theorem. So the first thing you would do when you see something like this is you would probably try to square it and do Cauchy-Schwarzes several times. So if you do something like this, then you get a statement of the following form: expected chi of x minus 1 to the p of x. This is at most 2 to the minus n over 2 to the d. This is the kind of statement that you would get if you took such a statement, you raised it to a sufficiently large power, did a lot of Cauchy-Schwarzes very carefully, and then at the end you would get you would have to bound some expression of the form chi of x plus ai product over I for various choices of ai. And statements and expressions of this form are bounded by the Weyl bound, and then plugging them black box in, this gives you a statement of this form, which for d being around log n is or smaller is something non-trivial, but once d becomes larger than log n, it doesn't say much. Okay, so the approach that we'll take here is actually going to be quite different, and it's going to be related to a method from circuit complexity, the Rasburov-Smolensky method of proving lower bounds for arithmetic circuits over F2. So I'll say a few. So in this context, things can be stripped off and said without saying too much about circuits, but I do want to say a bit about it. So the model is so it's sometimes called AC0 parity, and it's also sometimes called bounded depth arithmetic circuits over F2. We already saw arithmetic circuits earlier in the workshop. So the model is very simple. You have gates which can do plus, and you have gates that can do times, and you have a whole bunch of wires, and all these wires carry elements of F2. Okay, and then you arrange them in a circuit, and it's bounded depth, and it's small size.
You also, sorry. So now there is no parity here, it's just the plus.
The plus is parity, and the times is multiplication, and this is exactly the same as what we call AC0 parity. Good. So
you can do it all by complementation.
And you can do all by complementation, adding 1 to something. Good. So consider a bounded depth arithmetic circuit over F2, and then we're asking the question. So let C be depth D, size at most 2 to the n to the O of 1 over D. Then the probability over x lying in f2 to the n that C of x computes the cubic residue symbol of x, or okay, maybe I'll give you another. The cube root of x is small. Oh no, let me go with the cubic residue symbol. So lambda of x is at most 1/3 plus n to the minus 0.1. Okay, where lambda of x is either 1 omega or omega square, depending on the coset of the perfect cubes which x lies in. Okay, so lambda of x is the function that the cubic residue symbol. It tells you whether it tells you which coset of the perfect cubes the element x lies in. It takes 3 different values. So what does it mean for a circuit of this kind to compute lambda of x? Well, maybe the circuit has 2 output wires, and it takes one of 3 different values depending on whether lambda of x is 0, lambda of x is supposed to be 1 omega or omega square. So by compute this function lambda, I don't mean anything very deep about complex numbers or anything. I'm just it should be able to distinguish between the 3 cases of what lambda of x takes. Okay, and so this particular claim is basically equivalent to this claim, that circuits of depth d and size 2 to the n to the order 1 over d cannot compute the cubic residue symbol on more than 1/3 plus a small fraction of 1/3 plus a little bit fraction of all of f2 to the n. Okay, and so getting it with probability 1/3 is very easy on a random x, just because you output 1 always, or you guess something. But but to get even a slight advantage, this cannot be done unless you have very, very large circuits. Okay, so this statement is basically equivalent to this statement, and one can try to prove it in either language, and it turns out that some arguments are simpler in this language, and in fact the main step of the proof will be inspired by things that happen in AC0 parity. Okay, so one now wants to prove a statement of this form. Yeah.
What happened to the parameter going between that interpretation and this?
What happened to the d parameter? So a polynomial can be computed by depth 2 circuit. So this statement implies that without a d. I mean, plug d equal to 2 into this statement, and it gives you that. And if you prove a statement like that, then by the Rasborough-Smolensky method of approximations, then it gives you a statement of this form. So it goes both ways, and there need not be a d in that statement. And and the degree being n to the 0.1 has to do with constant sitting inside this and this.
So this would apply to all polynomials of sparsity 2 to the n to the 0.1, not just of degree at most.
This would apply to all polynomials of sparsity 2 to the n to the 0.1, yeah, because you can compute them using such circuits, yeah. Okay, good. So now in order to prove a statement like this, I want to say that it actually suffices to prove a statement which is seemingly much weaker, which is that, so for all c as above or below, maybe that's weird, as there, the probability over x in f2 to the n, that c of x computes lambda of x, is less than 0.99. So this formally is, proving a statement like this is formally weaker than this supposedly, but there's a trick called random self-reduction, which if you can compute it on 0.99 fraction of the inputs, then you can actually, if you can compute it on 1/3 plus n to the minus 0.1 of the inputs, then you can actually compute it on 0.99 of the inputs. And I'll just explain that in a second, but it's a very neat trick. So if we're given C computing lambda on 1/3 plus n to the minus 0.1 fraction of f2 to the n, then let me make a circuit C that gets it on 0.99 of the inputs. And the idea is just to use the multiplicativity of lambda. So consider the new circuit C tilde, which on input x does the following. Okay. C tilde of x is, so I'll just say it in quotes, so compute C of x y1, c of x y2, x times y2, dot dot dot, for several choices of yi, c of x y n to the epsilon, 0.1 maybe. So if you have a circuit that computes it right on 1/3 plus 10 to the minus 0.1 inputs, take that circuit and apply it to various random shifts of your input x. Look at what C tells you on all those inputs, and because C is supposed to be computing lambda, and lambda of xy is supposed to be lambda of x times lambda of y, this should be telling you something about what this should be telling you what lambda of x is. Okay, so compute all these things and take majority.
Do you want yi cubed? Because you want to maintain the value of...
Right, so it's not take majority, good. So compute that divided by lambda of yi, y1, lambda of y2, and so on.
So you have to be able to sample random elements with their lambda.
That's right, but this is a non-uniform reduction, so I'll just hardwire the yi's in. So I just need to know that there exist yi's and choices for the lambda of yi's for which such a reduction can hold. Any questions, anyone? Yeah?
If you multiply with y and then you divide, then this x times y divided by lambda, it might not be uniform. Are you sure it's uniform? Do you need it to be uniform?
Do I need...
Because the assumption is only on random elements.
Right, so this better be uniform, right? But I don't see, why should it be uniform? I mean, you're dividing again by lambda.
No. You compute the C and then divide.
So compute C of x yi.
Oh, yeah.
And then divide by lambda y. And even this has a small issue with it, but it's too fine a granularity for anyone to object probably. Yeah, okay, good. So but this is the rough idea, huh? I'll tell you anyway. Oh, okay, right. So there are three possible values for what lambda is. It could be that but none of them is a complete majority. So there's a little trick where you, instead of taking x times yi, you do x squared times y, and you do some hiding. But in principle, this is what you're trying to do. So compute C on many different shifts of x. So C of x y1, C of x y2, etc. This is supposed to be lambda of x, if C indeed work correctly, and then take majority or plurality or something. Okay, and this is something that can be done by a simple circuit because you have only n to the 0.1 such values which you want to take majority of. Okay, good. So we've now reduced ourselves to a situation which is like this. We want to show just a very, very weak average case lower bound on the computation of lambda by arithmetic circuits over by arithmetic circuits over F2. Okay, so for this we'll
so this randomized reduction is already an obstacle if you want to prove an exponentially small correlation.
This randomized reduction is the obstacle, in fact, for proving the
But if you could prove the 99% bound for circuits that have a majority gate on top and then is it 0,2, then you could run the reduction with an exponential number of y's.
Right. That.
No, so I didn't get this. By an exponential number, doesn't the size blow up?
So if you prove the 99% correlation for circuits that are acid zero parity but are allowed to have a majority gate on top, that counts as 1.
Right, but there are several inputs, right?
But all those C's you can invoke from the other circuit.
So there's just one copy of C.
Uh-huh.
No, there are 2 to the n to the epsilon copies of C.
Right,
Each of size 2 to the n to the
so
epsilon.
then the size is really large, right? For the
It's
circuit?
still 2 to the n to the epsilon.
Okay.
Okay, good. So now we need to prove a normal lower bound without any emphasis on the probability of success, just 0.99 probability. Okay, good. So now I'll give a very, very high level sequence of observations that motivate how one proves a lower bound of such a kind. So this is really what happens behind the scenes in the Rasburov-Smolensky circuit lower bound method, but I'll say it in very, very, very high level stuff. Okay, so I'll make an observation. Not all functions have low complexity. For whatever complexity means. Okay, that's hard to argue with. Okay. Huh?
It's hard to argue against.
Oh yeah. Good. So so now I'll make a definition. I'll say a function is versatile if, with its help, you can compute all functions. F is versatile if with F can compute all functions. Okay, easily, let's say. So that's a definition. That's also hard to argue with. Okay, so I'll put these two together and I'll make the main observation that will give us a proof that so a function, if a function is versatile, it cannot have low complexity, because if it did, then using it you'd be able to compute all functions easily, and then but all functions don't have low complexity. Okay, so versatile functions have high complexity. Okay, and so the final step is a lemma that lambda of x is versatile. Okay, in some sense, I have to make everything formal, and at this point, we have a lower bound. Lambda cannot be computed easily. It does not have low complexity. Okay, so I'll end by giving you the statement, at least this part of the talk, by giving you the statement of what does it mean that lambda is versatile, and then. Okay, so this is lambda is versatile. Okay, and this is just this is going to be a proper, cleanly stated statement, unlike this argument over here. So, here's what the claim is. So, for all functions f, from f2 to the n to f2 to the n, I can use lambda to compute f easily. So this is what I mean by that. So there exist functions g and h from f2 to the n to f2 to the n of f2 degree. This is something I have to define now. At most n over 2, such that f is equal to g times lambda plus h. So is the statement of this clear? For every function f, there are two functions g and h of low degree in some sense. So this f2 degree is not your usual notion of degree, but it's some kind of low complexity-ness measure, such that that function f can be written easily. It can be computed easily using lambda. Okay, so all I need to say now is what f2 degree means, and then I have to correct the statement to be actually true. So f2 degree is of a function g from f2 to the n to f2 to the n is the maximum degree. So what do we do? So I'm going to write f2 to the n as f2 to the n. I'll write this other f2 to the n also as f2 to the n. That's just choosing a basis. Then this g becomes a collection of maps, n maps from f2 to the n to f2 to the n. Right, so it becomes a collection g1 up to gn from here to here, and it's the maximum degree of gi.
Each gi is a map into f2.
Each gi is a map into f2. That's right. Right. So then write gi as an element of f2 x1 up to xn. You write it uniquely as a low degree polynomial over f2, and take it the maximum degree of gi over all the i's, and that is what is the f2 degree of the function g. And it's easy to see actually that this is independent of how you chose basis in all these choices. Okay, so it is a well-defined notion for functions independent of how you defined all these bases. So the maximum that the f2 degree of a function can be is n. Having f2 degree n over 2 is remarkably, it's a low complexity property. So the statement is every function f can be written with the help of these low complexity things g and h this way. Okay. And good. So this is not exactly correct. So one way to fix it is that most functions can be written like this. Another way to fix it is but then there's also some e, and e lies in some low dimensional space, which and we don't even need to know how low the dimension is. So the fact that it's coming from a low dimensional space is a sufficiently good statement of versatility. So with a statement like this, along with ideas from the Rasborov-Smolensky method of one can show that the function lambda cannot be approximated by low degree polynomials, cannot be computed by small arithmetic circuits, and we get a statement of that form, that lambda cannot be computed by arithmetic circuits on 0.99 fraction of the inputs, and then that fed into the random self-reduction, and then it gave us a final bound. Okay, so good. So any questions about this statement? Okay, and so let me also I'll also state the main lemma that goes into that lemma, which it's just a curious additive combinatorial lemma that I've never seen a question like this before. I don't think I'll ever see one like this again. It just happened to be the question that needed to be studied. So here is the world. You have z 2 to the n minus 1, and okay, so let m sitting inside z 2 to the n minus 1 be integers with base 2 Hamming weight. So meaning you write it in base 2 and look at its Hamming weight. At most n over 2. Okay, so the size of m is about half of z 2 to the n minus 1. Okay. Now consider alpha sitting inside z 2 to the n minus 1, alpha being 1/3. So 1/3 is an element of z 2 to the n minus 1. Let's say 3 does not divide 2 to the n minus 1. So 1/3 is an element of it. It actually looks like 1 0 1 0 1 0. Okay, this is how it looks in base 3, in base 2. Okay, then the claim is the following: the size of m union m plus alpha is what do you think the size of m union m plus alpha is?
M is half, yes?
M has size half of 2 to the n. That's right.
M plus union m plus alpha.
M plus alpha is you take that set and you add to it this particular number.
So
Addition is mod to the n minus 1.
Addition is mod 2 to the n minus 1, like in z 2 to the n.
Addition is coordinate wise.
No. It's the integer addition mod 2 to the n minus 1. That's what makes it tricky. Yeah. So my first guess was, they have nothing to do with each other. So bam, 3/4. I think that's a pretty good guess. So it's not. For this particular alpha, it's some 0.837. Okay, so it's no rational number, I know. 0.83 times 2 to the n, and right. And so the basic question and the basic So and the lemma that one needed was that this is at least half plus epsilon times 2 to the n. And the same thing holds for any periodic number. If you take any integer here, which is basically a rational with small denominator.
Half plus epsilon, but you said it's actually more than 3/4.
It's more than 3/4 for that particular number, but for other numbers it's less than 3/4, and it has its own. There's a whole world of numbers out there. Right. So, but for rationals with small denominator, where the denominator is not 1, this size is always at least half plus epsilon times 2 to the n. And somehow this is exactly what gives you the versatility. Okay, good. So that's all I'll say about this first statement. Yeah. So I don't have so much time. I just realized. So let me say very briefly a few things about the second statement. This was the fact that some functions like trace x to the 7 are unbiased when you restrict them to low-dimensional subspaces, provided there's no subfield lying around. So the usual way one proves statements of this form is through the Sum-Product Theorem, which is the number one theorem for proving things in the absence of subfields. So somehow this proof that this theorem that I'm talking about, so this actually joint work with Ali Ben Sasson, this theorem that I'm talking about now uses the absence of subfields in a very roundabout way, which so it's still puzzling to me as to why it even worked. So here is what the statement is. So let A be sitting inside F2 to the n. It's an affine space. So first of all, look at the polynomial product over all alpha in A, x minus alpha. Okay, and let's call this P sub A of x. Okay, so it's an elementary fact that this is actually of the form I going from 0 to dimension A, ai x to the 2 to the I. There are very, very few monomials that show up in this product. Only dimension A, many of them. And in fact, PA of x is a linear polynomial. It's additive. Okay, so it also turns out that there is a polynomial QA of x such that the image of QA is equal to A. So this was a polynomial which was a linear transformation, in fact, whose kernel was the set A, the space A. Now I'm giving you a linear transformation whose image is the space A, and its degree will also be as low as possible given this constraint, with QA of x equal to some I going from 0 to n minus dimension of A of bi x to the 2 to the I. So there is an additive polynomial of as low degree as you could hope, whose image is A. Okay? And these polynomials are quite related to each other. This is called the kernel subspace polynomial. This is called the image subspace polynomial. And good. So I won't go into the proof of that theorem. Maybe I won't even say how anything fits in. But I'll give you the statement of the lemma that detects the absence of subfields. This is always the trickiest part of a proof. What step of your proof is going to take advantage of the fact that A is not lying inside a subfield? So I'll make just that statement. Good. So QA of x is it's B0 plus B1. B0x plus B1 x square plus up to Bn minus dimension A. Okay, let me call that D. P n minus D x to the 2 to the n minus D. Good. This is how QA of x looks. So here is the main lemma about subfields. If A is not contained in alpha times so f2 to the j plus beta for all j. So if A is not contained inside an affine shift of a strict subfield, then you cannot have you cannot have a long run of zeros in the coefficients of QA. Then in every I sitting inside 0 up to n minus d with size I at least d minus 1, there exists some I in I with bi not equal to 0. So this is the image subspace of polynomial of the subspace A. it has some coefficients. Why does this polynomial exist? I don't know. No, I do, but that's irrelevant for this statement. It has some coefficients. These coefficients cannot have too many zeros amongst them in this particular sense. There's no long run of consecutive zeros in the coefficients, and right. And and this is the statement. This right. It exactly detects when A is contained inside a subfield. If A is contained inside an affine shift of a subfield, then you will see such a sequence of zeros. If A is not contained, then you do not see such a sequence of zeros, and thus and so this lemma enables you to distinguish between the presence of a subfield and the absence of a subfield in relation to A. So in one line, how does QA of x show up in the statement that trace x to the 7 is unbiased on the subspace A? So here is what the picture is. So we have f2 to the n. This is a big space. We're looking at the map. The map I was looking at was trace of x to the 7. So there's this initial map which sends x to the 7. Then there's another map which maps it down to f2, which is the trace map. And A sits somewhere here. And I want to show that on A, the composition of these two maps gives you some kind of balanced function. So what we introduce into this is the new field f2 to the n, and this is the map QA. Remember, the image of QA is A. So we have the map QA mapping all the way to A. Then we compose this. And so so we want to say the net composition of all these maps when mapping from f2 to the n all the way to f2 is non-constant, and it's unbalanced. And in particular, it's non-constant. So the kind of polynomial that you need to analyze is trace of QA of x to the QA of x to the 7. And you want to understand its behavior on the field f2 to the n. So you take this polynomial mod x to the 2 to the n minus x, and if you can show that this particular polynomial has a non-zero coefficient, that already means that this polynomial is non-constant. And once you have that it's non-constant, then there are other ways of showing that it's unbiased. So I won't mention that, but how do you show that this polynomial has a non-zero coefficient? Well, you open it up and look at all the coefficients that you get, and it's a big mess. And so by default, you wouldn't hope to be able to prove anything about it, but somewhere you want to show that something has a non-zero coefficient, and the lemma that comes in to save you is this particular thing. It tells you that there aren't too many zero coefficients lying around in some sense, and this lemma fortunately uses the absence of subfield. So so it gives you exactly the kind of statement you want. Good. So that's all I'm going to say about this. Any questions? Yeah.
So this is almost an affine extractor, right?
So this is an affine extractor. Yeah.
Well, there is this problem of well, if it is a subfield.
What if there is a subfield?
If A, like if your source lies on a subfield, then well,
then what happens? So you choose n to be a prime, and then it gives you an affine extractor. Yeah. So that there are no subfields, for example.
How does the large enough dimension come into play here?
Where?
So I thought you assumed that the dimension
A
right. Looks like
right. Well, when you open it up, I told you it's a big mess. So in order for the mess not to be too big, you assume that A is big.
Other questions? Thanks, yes.